Hello, let's solve some problems on waves. Let me read the first one. So, in a horizontal tight string, one of the ends is attached to a wall and the other goes through a pulley where there is a mass m hanging from it. We generate standing waves on the string. What mass m prime do we need to add to m so that the frequency of the new sixth harmonic be equal to the frequency of the old seventh harmonic? So what does it mean? So we have that string and we have a mass hanging here because of the tension, and the relationship between the tension and that frequency, we're going to have standing waves. So if you change the tension, then the wavelength of the standing waves is going to change, because by changing the tension, you're changing the velocity. The frequency is constant and the density of the string is constant. So because the tension is equal to mu times velocity squared, you change the tension, you change the velocity. Velocity is frequency times wavelength. If the frequency is constant by changing the velocity, therefore you are changing the wavelength. So you are changing the tension until, with the same frequency, you find, instead of the seventh harmonic, the sixth harmonic. You know that by increasing the tension, you are decreasing the number of notes. So you can start with those 7, then you increase the tension, you go and see there will be a particular tension where you have those the sixth harmonic. You can increase, go to 5, 4, 3, 2, 1, finally just 1. So let's go and solve this problem. We want that the frequency of the new sixth order or harmonic is equal to the frequency of the seventh old harmonic. So for standing waves on a string, we have that the wavelength is equal to 2 times the length, 2L, divided by n, where n is just an integer number, 1, 2, 3, 4, 5. So lambda of the sixth harmonic is going to be L over 2 times 6. Lambda of the seventh harmonic is going to be L over 2 times 7. Also, for standing waves on a string, we know that the force of tension is equal to mu times velocity squared, where mu is the density, the linear density of the string. So we have that the force of tension, therefore, is equal to mu times lambda squared frequency squared. Because the force of tension is just the weight that we're hanging there, we have that for the old tension is equal to mass m times g, and for the new one we have m plus m prime times g. So we can write these two equations, the old situation and the new situation, and we have that mg is equal to mu times L7 square f square, and m plus m prime times g is equal to mu times the wavelength of the sixth harmonic times frequency, everything squared. So we divide one by the other one and we get that m plus m prime divided by m is equal to lambda 6 squared over lambda 7 squared. We solve for the mass prime, that is what we're looking for. M prime is the ratio lambda 6 squared over lambda 7 squared times the mass minus the mass. Then we factor out this mass, so it's mass times parentheses L6 squared over L7 squared minus 1. Because for standing waves, the relationship between the length and the wavelength is given by lambda sub 6 is 2 times L over 6 and lambda sub 7 is 2 times L over 7. We substitute the wavelength by this, and then we get that the mass prime is equal to the mass times 7 squared divided by 6 squared minus 1, which gives us that the m prime is 13 over 36 times m. Let's go and solve this other problem now. In this problem we have the following situation. So you are looking for a spy in a warehouse full of tubes open on both ends. So the tubes are open at both ends. So suddenly you hear one noise and you pull out your sonic ranger to tell you that the frequency of that sound is of 512 Hertz. You measure the temperature of the warehouse and you find that is 20 degrees Celsius. You do some quick back of the envelope calculations and look at the catalog of tubes at that warehouse, and you find that the tubes are only of 3 different lengths: 20.5 centimeters, 33.5 centimeters, and 46.5 centimeters. Now, in which section of the tubes is this pi? Okay, so in this case, we know that if you hear that particular frequency, so you need to find what tube allows that frequency to be resonant in. So because we have a tube open in both ends, not all the frequencies are going to be resonant, but one of these, or at least one of those three tubes open at both ends, should be resonant at that particular frequency. So what I'm going to do is calculate the wavelength of that particular sound. Remember that the wavelength is just the velocity divided by the frequency, and the frequency is what we have measured, and the velocity, we can calculate the velocity if we know the temperature, which we actually do. So first of all, we'll calculate the velocity of sound in that warehouse. Then I will calculate the wavelength, and then I will see that wavelength where it fits. Okay, so let's find first that wavelength of this sound. On the velocity, we know that the velocity is just 331 times the square root of t over 273, where t is the temperature in kelvins. So if I substitute that 20 Celsius into that expression, I found that the velocity of sound, the speed of sound there is of 343 meters per second. So from there, I can calculate the wavelength, which is just the velocity over the frequency. So 343 over 512, which is 67 centimeters. So that's the wavelength of the sound that I'm listening, I just heard. So because the tubes are open in both ends, that means that the wavelength allowed in those tubes is 2 over n times L, where n is just 1, 2, 3, 4, 5, any integer, and L is the length of the tube. So, okay, let's divide the wavelength that I just found over those three lengths, and let's see what I find. If I divide lambda over L, I have to find 2 over n, where n is an integer. So if I use L1, I find that lambda over L1 is 3.27, which I cannot write as 2 over n. If I divide lambda over L2, I find that that is 2, which, yes, it would be resonant for n equals to 1. That's the fundamental mode. If I divide lambda over L3, I find that that is 1.44, which cannot be written as 2 over n. So the SPI is in section L2. Let's solve the last third problem. This problem says an explosion takes place that is registered at a distance of 50 kilometers as a sound level of 50 dBs. Now, how many simultaneous explosions need to be done at the same point so that the sound level at those 50 kilometers turns out to be 70 dBs? We're going to assume that the sound propagates in a spherical wave and there is no loss of energy in the wave. Well, because there is a relationship between the sound level and the intensity, and there's a relationship between the intensity and the power, I'm going to first calculate what's the intensity at the beginning with just a single explosion of those 50 kilometers. Then, when I know the intensity, I will calculate what's the power delivered by one single explosion. Then, I will go do the same with the 70 dBs, calculate what is the power needed, and then we'll compare that needed power with the power delivered by a single explosion, divide one by the other one, and that number will be the number of explosions that need to take place simultaneously in the same place, so that instead of 50 dBs, that's going to be 70 dBs. Between sound level and intensity is beta is equals to 10 times the log base 10 of I over I naught. And I, which is intensity, is just the power of divided by the area. I will find the power of a single explosion first, which is beta, which is 10 times log base 10 of I over I naught. I solve for the intensity. I will say I sub 1 to this single explosion. So I sub 1 is equals to I naught times 10 to the power of beta over 10, which if I substitute, remember that I naught is just that reference intensity of 10 to the power of negative 12 watts per square meter. So I get that the intensity of that single explosion is 10 to the power of 7 watts per square meter. That's a spherical wave, therefore the area is 4 pi r squared. So the power delivered by one single explosion is I times A. I substitute that A by 4 pi r squared. I substitute the data and I get that the power of a single explosion is 3.14 times 10 to the power of 3 watts. Now, to have that as 70 dBs at the same distance, the intensity is, I will call it I sub 2, is 10 to the power of negative 12 times 10 to the power of 7, which is 10 to the power of negative 5 watts per square meter. So the power 2 is I2 times A, which gives 3.14 times 10 to the negative 5 watts, which happens to be 100 times greater than P1. So I need 100 explosions simultaneously and at the same place to go from 50 dBs to 70 dBs.